Hey, this is the sixth video in the solution architecture series. In my previous videos, I have explained how to collect the business requirement, how to functionally decompose a business problem into smaller solution components, how to design a solution component, what a bounded context and designing the bounded context using the model-driven design, choosing the suitable communication and integration style for the inter-process component communication, and we know each solution component should own its data, including its model architecture and management. We start with the data modeling. Usually, I start the data modeling from the very beginning when I am looking at the business problem and trying to functionally decompose it. At the same time, I start the data modeling. Data modeling is a visual representation of the whole information system. It shows how data are grouped and the relations among the data. Data can be modeled at various levels of abstraction. The process begins by collecting information about business requirements from the stakeholder and end users. Like any design process, database and information systems design begins at the high level of abstraction and becomes increasingly more concrete and specific. The process will start with a conceptual model, progress to a logical model, and conclude with a physical model. We can do data modeling of the entire system, that is, include all the solution components, considering it's not too big. Otherwise, for each solution component separately. Conceptual data models offer a big picture view of what the system will contain, how it will be organized, and which business rules are involved. Conceptual models are usually created as part of the process of gathering initial project requirements. Logical data models are less abstract, provide greater detail about the concepts and relationships in the domain under consideration. These include data attributes such as the data types and optionally their corresponding lengths, and show the relationships among entities. They can also show relationship like one to many, many to many, etc. Physical data models provide the schema for how the data will be physically stored within the database. As such, they are least abstract of all. They offer the finalized design that can be implemented as a relational database, including associative tables that illustrate the relationships among the entities, as well as the primary keys and the foreign keys that will be used to maintain those relationships. If the database chosen is non-relational, the physical data model will include or provide details accordingly. Physical models include database-specific details. We may choose conceptual and logical data modeling as relational, whereas we may choose physical as a non-relational. But for conceptual, try to create and show entities and their relations. While implementing it physically, we can make this implement in a NoSQL database. While doing this data modeling, I also try to take care of the normalization, especially when I'm at the physical state. So normalization is a technique of organizing data in multiple related tables to minimize data redundancy. Data redundancy is repetition of same data at multiple places, and this repetition of data at multiple places leads to storage insertion, deletion, and updating problems. I'm trying to reduce this. Whereas once I have done the normalization, sometimes I have to look now for denormalization. Denormalization is a strategy used on a previously normalized database to increase the performance. In computing, denormalization is the process of trying to improve the read performance of the database at the expense of losing some write performance by adding redundant copies of data or by grouping the data. Denormalization differs from the unnormalized form in that the denormalization benefits can only be fully realized on a data model that is otherwise normalized. You keep the logical design normalized, but allow the database management system to store additional redundant information on disk to optimize the query information. While at the logical level, I try to keep things denormalized, or even on the physical layer, on the design, I try to keep denormalized. But when I'm actually implementing the database, sometimes uh, actually at the physical design, I keep things normalized. When I'm implementing, I then decide where to apply denormalization for improving the performance. If you're using a NoSQL database, then like such as a document database, then which are supposedly built to store flexible denormalized data. We can use aggregate that allows us to store a business entity as one document or a key value pair. We also have an option to store transactional write data in relational data stores and maintain denormalized read-only data in NoSQL database. I was part of a bank and in which we had a lot of relational databases and there was a performance issues. So we introduced MongoDB as a NoSQL database and we created a lot of aggregates and denormalized view in that MongoDB, and it was called operational data store. It was used for in real time for performing the read operations. Those cut across many different databases. At the state of the logical data modeling, we can choose a data store or database, the standard relational database, or one among the NoSQL database. An informed decision is needed for physical design. We functionally decompose the application and decided on no data sharing. That is, each component is free to choose their database, and no component is bothered as the data is all through APIs. So one component doesn't bother what other component is choosing as a database, and all the data access from one component to other component is through APIs. Each component data can be structurally different. For some component, it can be relational and like SQL schema, and for the other component, it can be semi-structured like a JSON object, where each object can have a different shape. It can also have no defined structure like textual data for a full texture, textures, or a key value pair. A solution architect should choose the appropriate database for the solution component. I call it a purpose-driven database. So we have options like relational database, key value, graph database. These are some of the popular choices. There are more popular choices such as document database, in-memory database, time series database, and there are more databases. For example, there is an AWS bookstore demo app, and it shows the idea of using polyglot persistence, in which idea is using multiple data storage technologies to handle different data needs within one system component composed of multiple components. In that demo app, there is a product catalog. So when a user accesses the bookstore's web storefront, they might expect to see a list of products. Products typically contain unique identifier and the attributes such as descriptions, quantities, location, and prices. In a technical sense, the method for retrieving these attributes, these type of attributes, that is the access patterns, is often a key value lookup based on product's unique identifier. This means that an application can retrieve these other attributes when a product's unique identifier is provided. That's why Demo app uses a DynamoDB for the product catalog. There is also an option for consumers. Come to the bookstore, they want to locate the product they intend to buy or search through a catalog to find the next great read. And the demo app uses Amazon Elasticsearch as a database technology for this search functionality. Because Elasticsearch has a natural language capabilities, faceted navigation, and ranked results. So Amazon Elasticsearch helps customers quickly find the items they want in the product catalog. The demo app also shows a list of bestsellers. Now, bookstores users can see top 20 purchased books within a period. Amazon Elastic Cache for Redis provides exactly what is needed, including built-in in-memory data structures such as stored sets that allow the bookstore to create the best sellers list quickly and effectively. There is a social recommendation feature as well, which helps bookstore customers find more contextually appropriate content. In this case, content based on what their friends have purchased. A purpose-built graph database such as Amazon Neptune is a natural fit to navigate links in the data, enabling recommendations that are based on social connections and related purchase activity. While choosing a database, consider purpose and the functional aspect. Another aspect is CAP theory. We are talking about distributed systems here, in which network stores data on more than one node. And there are three important aspects. Consistency is first. So consistency is all clients see the same data no matter which node they connect to. For this to happen, whenever data is written to one node, it must be instantly forwarded or replicated to all other nodes in the system before the write is deemed as successful. Another aspect is availability, in which every request to the database receives error-free response. It may not contain the latest write, but database is 100% available. Partition tolerance is third aspect. It is a database system. That is, the database system continue to work even if one or more nodes fail. The theory is that it is practically impossible to achieve fully all three these aspects. That way, RDMS aim for consistency over availability and partition tolerance, whereas a NoSQL database will aim for availability and partition tolerance, and for consistency, NoSQL database will prefer eventually consistent, not a strongly consistent. A solution architect will know what is more important for the particular solution component and accordingly select the database. There are four more criteria and techniques which can be applied while choosing the most appropriate most appropriate database. In one project, I use Cosmos DB, which is a multimodal database. I'm sure there are more such databases. I've also seen one from Oracle. And the idea is that we can have just one database, and that database will have different set of APIs, such as it might provide also a relational API. It can also provide a key value API and a graph API, but it stores data in just one format. So a database has two things. One is obviously an interface, which is the API through which we access the data, and second is the storage part. Or we can say there is a storage and there is a compute part. So data is stored in the same way. It's some variant of key value, but data can be exposed through multiple interfaces. That is APIs for NoSQL, APIs for MongoDB, APIs for Postgres, and so on. So all solution components can just use Cosmos DB, whereas they might use different APIs as an access mechanism for the same database. Within the database, we can create multiple schemas, or we can create different instances to separate one solution component own data from another solution component own data. But overall, we reduce the burden that, okay, it's just one database from management perspective, cost perspective. Last decade, there has been this new pattern, CQRS pattern, that recommends separating reads and writes into different models using command to update the data and queries to read the data. For greater isolation, we prefer to physically separate the read data from the write data. In that case, the read database can use its own data schema that is optimized for queries, and if a separate and similarly write can use its own database. If the read and write databases are used, they must be kept in sync. Typically, this is accomplished by having the write model publish an event whenever it updates the database, and read data store updates its data model accordingly. For example, if we have multiple microservices, for example, order, kitchen, delivery, accounting, etc., each one uses its own database or data model that it finds most appropriate. Whereas we also have a requirement to publish order history, and for that we created a different service, order history service, for the purpose of providing the complete order history. Clients don't query now each of these services, order, kitchen, delivery, accounting, separately, but instead they just query to order history service and they get everything they want. And implementing such a service is not straightforward because it has to join data from multiple services. It has to pull the latest data. And one option is that this service can call the APIs of each service when it receives a request and then combine those response and send it. Another option is that order history service can maintain its own database. It populates its data whenever it receives an event, domain events from other services, and that it will be more performance efficient. Event sourcing persists the state of business entities such as order or a customer. So in previous example, I have shown that okay, that the 3-4 services, they have their own database and they might be using relational database, storing in just a typical way. whereas the order history service is taking more a event-driven approach, where in which it is storing it is receiving the events and storing the events and updating its view, which is readily, which it wants to make to readily available to all its clients. It is also possible that we can persist the state of business entity, such as order and customer, as a sequence of state-changing events. So we can either order service can have an order table in which each row can be unique order, and it can update the same order as the order state changes, or it can store it like events. Whenever the state of business entity changes, a new event is appended to the list of events. Application persists events in an event store, which is a database of events. So the store has an API for adding and retrieving the entity's events. The event store also behaves like a message broker. It provides an API that enables event services to subscribe to these events. When a service saves an event in an event store, it is also delivered to all the interested subscribers. The application can reconstruct an entity's current state by replaying the event. Instead of storing just one order row in database, updating it later, we are storing a new event for every change in order entity. If need is to return the order entity or an order row, then we can construct it on the basis of these events. Some entities such as customer account, etc., can have large number of events. In order to optimize the loading, an application can periodically save a snapshot of an entity's current state. To reconstruct the current state, the application finds the most recent snapshot and the events that occurred since that snapshot. As a result, there are fewer events to replay. I use this pattern while designing an onboarding journey. So journey had save and resume feature in which prospect who is not yet customer, who is just completing the onboarding journey, can complete the journey partially and resume the journey later. After the prospect completes any step of the journey, I would generate an event and store it in the DynamoDB database. For analytical reasons, we also had a prospect read-only RDMS database in which I used to maintain a single row for each prospect and updated every time I received an event from the DynamoDB. We can take event sourcing to the next level, in which we can capture data in real time from all the event sources like databases, sensors, mobile devices, cloud services, social media, and the software applications in the form of streams of events, and store these event streams durably for later retrieval. We can even route these event streams to different destination technologies that needed. Kafka is designed for moving large and continuous streams of data fast. It is different from previous message brokers in which messages were moved from point to point, producer to consumer reliably with guaranteed delivery and acknowledgement, along with mechanisms for retry for failed deliveries such as in JMS. In Kafka, in contrast, every message is persistent and stored on disk. To improve performance, Kafka does sequential access, not random access. And it doesn't care about point-to-point integration much. It doesn't care much about this delivering one message from here to there. It just stores these events. It guarantees storage. Kafka is an event router, but it's also a long-term durable event storage, which makes it suitable for event sourcing architecture. Kafka holds the streams of persistent events, and consumers consume events not only in real time, but also they can consume the historical events. Consumer can buffer events and build SQRS style views. Data is shared as streams which can reside in the log for a very long term. But the mechanism for manipulating that shared data is embedded inside each bounded context that is inside each service. There are several pieces of the streaming architecture, and Kafka plays an important role in this architecture. That is source events from sources to that we can source the events from sources to Kafka, either using connectors or use a push-based model. We can store events temporarily or for a long term. And we can load or pour the events into databases so that consuming applications can query the current state. We can transform the events using the stream processors such as Flink and Spark and create a new stream. as well as we can have microservices subscribing those to those events and updating their own databases as required. As this streaming world grew up and as the Kafka ecosystem got mature, solutions within Kafka platform for each piece emerged. KSQL DB adds a compute and query layer on the top of the Kafka storage layer. Now we can actually build an entire system which can have multiple components, and we can have just one solution, Kafka, and we can use it for everything. We can have a complete event-driven architecture. Everything happens to event streaming. Each bounded context can actually create views according to whatever they format they want. But all the events from everywhere comes to just one Kafka. We can create materialized caches, we can have streaming ETLs, we can respond to events, we can actually store events for lifelong. All the use cases can be built inside the Kafka plus KSQL DB. But still, most architects and there are guides who consider message queues and topics and even Kafka as a temporary storage. And they prefer a more time-tested solution, and also they want to keep a separation of concerns. That's why they will still prepare a centralized data storage, such as a data warehouse, to aid the data analysis. So each solution components can own their databases, and from there we can extract the data, transform the data, and load it into the data warehouse from where we can generate the reports. But like actually data warehouses face the problems of volume, velocity, veracity, etc. because now there was more non-structured databases and we can't actually transform all the data into one structure inside the data warehouse. And data warehouse was the first generation of data analytics platform. The second generation data analytics platform, data lake, it overcame the limitations of data warehouse. It offloads all the raw data into low-cost storage systems with file API that hold data in the generic and usually open file formats such as Apache Parquet. And initially, the term data lake was often associated with Hadoop-oriented storage to describe any large data pool in which schema and data requirements are not defined until the data is queried. So we changed the mechanism from extract, transform, load to we can just extract and load and then transform the data. First let's bring the data all together at one place in the data lake, and then let's transform it according to the requirements. And companies still were using both data lake and data warehouses, so they were trying to pull all the data in the data lake and then again actually transform the data and put into data warehouse from where they can generate reports, they can do data analysis, they can do data science, etc. They can run machine learning algorithms either on data warehouse or they can run it on the data lake as well. But last few years there has been a lakehouse concept, and a lakehouse combines both the data warehouse and data lake benefits into one. So we can run actually SQL APIs, metadata APIs, we can create data frames, etc. Everything, metadata, indexing, caching, everything on the top of data lake. So I covered a lot of concepts related to data architecture that a solution architect may face. I will create a few more videos in this series optionally, and thank you very much for watching the video. If you like it, then please subscribe and like the video. Thank you.